String theory takes you before the Big Bang, before Genesis itself.
The beauty and allure of string theory lie in its ambition to be the theory of everything, providing a unified explanation for all fundamental forces in the universe. String theory proposes a departure from conventional beliefs about atoms and suggests that the fundamental building blocks of the cosmos are tiny vibrating strings rather than point-like particles. The central idea is that these one-dimensional strings vibrate at different frequencies, akin to the strings on a musical instrument. The vibrations of these strings give rise to various particle types observed in the universe, such as quarks and electrons. String theory also introduces the concept of extra dimensions beyond the familiar three spatial dimensions and one time dimension. Notable advocates of string theory, such as Michio Kaku, contribute to its popularity by providing accessible explanations and captivating discussions about the theory's potential. However, despite its beauty and ambition, string theory faces significant challenges and lacks experimental verification. The absence of experimental confirmation poses a barrier to the widespread acceptance of string theory as an accurate description of the universe. While the theory has mathematical elegance and offers a unique perspective, it remains in a state of theoretical speculation until experimental advancements can push the boundaries of current technological capabilities. In the pursuit of understanding the universe, scientists continue to explore alternative theories and approaches. Recognizing that the beauty of a theory should ideally be complemented by empirical evidence and experimental validation. As of now, the question of whether our universe is truly made up of strings or atoms remains an open and intriguing area of investigation in the realm of theoretical physics.
Plus, the Standard Model only describes 4% of the matter-energy content of the universe. Just 4%. Dark matter makes up 23%. Dark energy makes up 73%. So a huge chunk of the universe is missing. And that's why some of us, like myself, believe in something called string theory. String theory, the Standard Model, including the Higgs boson, is nothing but the lowest octave of a vibrating string. And dark matter, which makes up 23% of the universe, is nothing but like the next vibration up, the next octave of the string. And then dark energy, well, dark energy, it takes place when you break the symmetries of the superstring. So string theory is the only game in town which has the ability to be really a true theory of everything. So the next step is to try to find dark matter with the Large Hadron Collider. That could go a long ways toward either proving or disproving string theory.
String theory is a theoretical framework developed in the late 20th century that aims to describe the fundamental building blocks of the universe. It seeks to unify quantum mechanics and general relativity by proposing that the fundamental entities in the universe are not point-like particles but rather one-dimensional strings that vibrate at different frequencies. The historical development of string theory can be traced back to the late 1960s and early 1970s. With key contributors such as Leonard Susskind, Holger Beck Nielsen, the Nobel laureates Leonard Brink, Peter Goddard, and Gabriele Veneziano. These scientists laid the groundwork for understanding the vibrational patterns of strings and the mathematical elegance that underlies the theory. One of the main departures from traditional point-particle theories is that string theory introduces the concept that particles are not point-like but are tiny vibrating strings. These vibrations give rise to different particle types, such as quarks and electrons. Additionally, string theory proposes the existence of extra dimensions beyond the familiar three spatial dimensions and one time dimension. These extra dimensions play a crucial role in shaping the vibrational characteristics of strings. The potential benefits of string theory are numerous. It aims to provide a unified theory of physics, incorporating all known fundamental forces: gravity, electromagnetism, weak nuclear force, and strong nuclear force. By doing so, string theory seeks to offer a comprehensive view of the cosmos and address long-standing questions about the nature of dark matter and dark energy. Despite its promise, string theory faces several challenges and limitations. Lack of experimental verification. String theory currently lacks empirical evidence to support its predictions. The required energy scales to observe the effects of strings directly are beyond current experimental capabilities. The landscape problem. String theory introduces a multitude of possible configurations, each with its own set of physical laws and properties. This lack of uniqueness complicates the task of identifying the specific version of string theory that accurately describes our universe. Complexity and mathematical rigor. The mathematical framework of string theory is complex, requiring advanced mathematical concepts and techniques. The intricate mathematics may limit the number of researchers who can actively contribute to its development. Extra dimensions. The introduction of extra dimensions in string theory is a distinctive and intriguing feature, but it also brings about significant challenges. These challenges encompass both experimental verification and conceptual understanding. Experimentally, the proposed extra dimensions are postulated to be compacted or curled up at scales much smaller than those currently accessible by experiments. The microscopic nature of these dimensions demands experimental precision beyond our present technological capabilities. Detecting or confirming the existence of these extra dimensions requires advanced tools and techniques that can probe scales well beyond what is currently achievable. This poses a considerable barrier to providing empirical evidence for the existence of extra dimensions. Conceptually, the idea of extra dimensions challenges our intuitive understanding of space. In our everyday experience, we perceive three spatial dimensions: length, width, and height, and one time dimension. String theory proposes the existence of additional spatial dimensions, potentially hidden or compacted, beyond our direct perception. Understanding how these extra dimensions interact with the familiar three spatial dimensions and influence the behavior of strings adds complexity to the overall framework of string theory. In summary, while the introduction of extra dimensions in string theory is a fascinating proposition, the challenges associated with experimental verification and conceptual assimilation emphasize the need for innovative approaches and advancements in both theoretical and experimental physics to explore this aspect of the theory. Uniqueness. The lack of uniqueness in string theory is a significant characteristic that distinguishes it from traditional theories. Instead of a single, definitive formulation, string theory encompasses multiple versions and formulations. This diversity of string theories introduces ambiguity and challenges the conventional scientific expectation of a singular, all-encompassing theory that precisely describes the fundamental nature of the universe. This absence of uniqueness poses questions about which, if any, version of string theory aligns with the observed phenomena in our universe. Researchers face the challenge of determining which assumptions, principles, and predictions from the various string theories accurately reflect the reality we observe. The multiplicity of formulations complicates the task of identifying the correct version that provides a comprehensive understanding of the cosmos. This lack of a unique solution is one of the distinctive features of string theory, contributing to both its appeal and the challenges it presents in the pursuit of a unified theory of physics. Despite these challenges, string theory remains a fascinating and actively researched area in theoretical physics. It is not the only contender in the quest for a unified theory, as alternative approaches such as loop quantum gravity, supersymmetry, causal dynamical triangulations, emergent gravity, modified Newtonian dynamics, and quantum loop cosmology offer unique perspectives on understanding the fundamental nature of the universe. Each of these alternatives comes with its own set of principles, challenges, and implications. Thank you for watching another episode of Space Odyssey. While you are still here, don't forget to like and subscribe.